Ready? Uh, Welcome everyone to a new session of our Categories seminar. Today we have the pleasure and honor of having Eric Samperton from University of Illinois and now with a position in University of Purdue, who will be talking to us about his work on anions, defects, and computational complexity. Before starting, if anyone wishes to ask a question during the talk, please unmute yourself or ask the question in the chat. If you don't feel comfortable asking your question in English, please ask me in Spanish, and I will be very happy to translate for Eric. Students are especially encouraged to ask questions. So please, Eric, thank you very much, and go away.
Yeah, thanks, Carlos. Yeah, so I've only really planned out in any detail like a third of this talk, in part because I want to leave time for people to ask questions and to kind of let things develop where they're going to go. So my understanding is you've had a bunch of people recently in the seminar speak about different types of fusion categories and such. So I hope to get to that stuff towards the end of the talk, but I really want to lay out carefully some of the definitions and ideas involved in complexity theory, because I think that will be completely unfamiliar to most people here. And, it's necessary to understand what I'm trying to do with fusion categories later anyway. So, but to motivate this, I kind of want to, this stuff will tie into topological quantum computing, but I want to start with kind of elementary motivations, okay? So can ask, why do we do knot theory, right? We do knot theory because we want to understand knots. And one way to make that precise would be to find good invariants of knots, right? So here, by an invariant of a knot, I just mean some function that takes a knot diagram and spits out some number. Maybe it's a complex number, maybe it's an integer, maybe the invariant takes values in something other than the complex numbers, but whatever, we're not going to fuss too much about that. But it's an invariant in the sense that, well, this function, it takes a knot diagram and gives you a quantity, but that quantity only depends on the topology of the diagram, meaning if you have two different diagrams that represent isotopic knots, so they're related by Reidemeister moves, then the invariant should take the same value on those different diagrams, right? That's what it means to be an invariant. And just as knot theorists, our goal is to find good invariants, right? We want to be able to distinguish lots of different knots from one another using invariants. And one thing that makes an invariant good is if it's a complete invariant, right? So by complete, I mean it distinguishes all different knot types. Okay, so if you have two different diagrams that represent distinct knots, then a complete invariant will give you different values. Okay, so of course, the real dream would be to have a really good complete invariant of knots. Now, we don't know if such an invariant exists, but we can start asking, what do we really mean by a good invariant? Whether it's complete or not, what does it mean to be good? But, well, to make that precise, we need to use the language of complexity theory. An invariant I consider it to be good and actually practically useful if we can efficiently compute it. Right? So it can't just be some abstract invariant. There actually needs to be an algorithm to compute the invariant from a given diagram. And to make it a good invariant, there should be a good algorithm in the sense that we can quickly compute the invariant. Okay. So this is all just supposed to be some elementary motivation for what I think is an important question. If you're a knot theorist and you have an invariant that you like, then what you should ask is, what is the computational complexity of that invariant? Okay. And I'm going to spend most of the talk unraveling what this means. Okay. What this question is really getting at. And just to foreshadow, there's two things involved in understanding the computational complexity of any function. First, you need to have upper bounds on the complexity. And an upper bound on the complexity of a function is, in other words, it's an algorithm. Okay, you want to say, well, I have some algorithm that runs pretty quickly. That would be an upper bound on the complexity of the function. And then you need lower bounds, okay? And these are maybe less familiar to people who haven't seen theoretical computer science before, but these are what are sometimes called hardness results. And a lower bound on a problem, they're often conditional. You often prove lower bounds on the complexity of a problem saying, what do I mean by lower bound? I mean like, oh, you have some some theorem that says there is no algorithm that does better than exponential time or something. Okay, but one issue is that lower bounds are often only proved conditionally, because we, in theoretical computer science, we don't know things like whether P and NP are different. These are two different complexity classes, and lower bounds are usually proved assuming things like P and NP are distinct. Okay. So I'm going to say some things about, general things about what these things really are, and then I'm going to start talking about. I'll transition to knot theory again, okay, in this talk. So I'll go through some. I just try to give a little bit of motivation, elementary motivation, to why we should care about the computational complexity of invariance of knots, and I'm now going to start on some background definitions involved to unpack all of this. And then I'm going to start really getting into some background on algorithmic knot theory. And then I'm going to talk about my work on group theoretic invariance of knots. And then time permitting, I'll get to the anyons and the defects in part 3 and topological quantum computation. Okay, and say some things there, but I'm not sure if I'll make it. So anyway, some background. So I want to give a little primer on complexity theory. And for this, we need some definitions. So you see over on the right here, these are a bunch of different complexity classes and their relations, but don't stare at this too quick. Yeah, let's go through some definitions. So in complexity theory, we study decision problems, okay? So decision problem is simply any function, usually denoted L for language. There's a long history for why they're called languages, having to do with logic and stuff. But a decision problem is a function that takes something from the set of bit strings. So this here is just the set of all bit strings. So I have, the union over all positive integers k of 0, 1 to the k. So 0, 1 to the k, this set is just all the bit strings of length k. And then we're taking the union of all of those over all lengths k. So this is just a set of all possible bit strings. And the decision problem takes a bit string and outputs either a 0 or a 1. 0 we interpret as no, and 1 we interpret as yes. Okay, so this is a decision problem. You're given a bit string. You just want to know, is the value of that decision problem yes or no for that given bit string? So this is all very abstract, but I'll give some examples in a minute. And something I want to say is that a bit string is here in this context, an input to a decision problem, which is just a bit string for us, is sometimes called an instance, because a problem isn't just a single thing. Like typically we have like a class of problems, right? Like I don't know, graph connectivity. You're given a graph, that's an instance of the problem, and you want to decide, is the graph a connected graph? So in that case, the graph is the instance, and the decision problem is answering either yes or no, depending on whether the graph is connected or not. Yeah. So I'll come back to that in a second. But we can also generalize instead of, so most of complexity theory is concerned with decision problems. And this is strictly for like convenience, right? It's convenient just to work with abstract bit strings and to look at functions that take abstract bit strings to just a single bit, 0 or 1. But you can generalize, and instead of looking at functions that take a bit string to yes or no, you could look at functions that take a bit string to another bit string. Okay, and here we have an input, an instance and we would call this a counting problem. And the reason why is because in a counting problem, we're taking a bit string and converting it to another bit string, but we interpret this bit string over here as a natural number in binary. Okay, so there's all kinds of counting problems in the world, right? Like given a graph, which you might encode as some bit string, you can ask how many connected components does it have, and output that as a number in binary. Okay, so that's an example of a counting problem, counting the number of connected components of a graph. Okay. So these are the elementary things that one studies in complexity theory, but one aggregates them into complexity classes based on algorithmic concerns. So again, this is all very formal and general, but a complexity class is simply any set of decision problems or counting problems. Okay, it's complete generality, but that's almost a useless definition. We are usually concerned with complexity classes that are defined by the existence of algorithms that meet certain resource constraints. Okay, so For example, you might only look at the decision problems that admit an algorithm that runs in polynomial time and the length of the input, okay? Or polynomial space or exponential space, things like this. So those are the interesting complexity classes, and it's theoretical computer scientists spend most of their life trying to distinguish and compare different complexity classes, okay? And they have a whole bunch of techniques to do that. Finally, another kind of elementary thing. So I told you that in the context of decision and counting problems, an element of the input, which is a bit string, is sometimes called an instance. Well, when we start talking about complexity, it's important to keep track of the size of an instance, okay? So in this case, if you just have a bit string, its size is just the length of the bit string. Okay. So for example, the bit string 10011, its size, I denote it by putting absolute value sign over it, is equal to 5. Okay. And note this would equal, if we think of this 10001 or 10011 as that, if we think of that as a natural number in binary, then the size of that natural number is log, okay? Log base 2 of that natural number. The length of the if you have a natural number, you write it in binary, its size is the length of the binary string, which is log 2 of that natural number. Anyway, so here's a bunch of complexity classes. I'm going to get into it in a second, but just to give you different relations, right? So complexity classes are sets of functions. So it makes sense to talk about whether one complexity class is contained in another, et cetera. So maybe the most elementary and important complexity class is P. These are polynomial time computable decision problems. So I'll say more in a second. So all of these are complexity classes that consist only of decision problems. I talked about counting problems, but I might not say much about counting problems later in the talk. So I'm just going to focus on decision problems. So all of these are different sets of decision problems, and they're contained in one another, right? So you've maybe heard of BQP. I'll say more about that one later. This is bounded error quantum polynomial time. I'm not going to get into that one yet, but I'm going to focus on these ones for now. Okay. So there's polynomial time. There's NP, which is non-deterministic polynomial time. There's co-NP, which is like the opposite class from NP. Then there's P space, polynomial space, and then there's X, which is exponential time. So I'm going to talk through some examples here. But just to reiterate that this is all very formal and abstract. We have bit strings, but at the end of the day, for us, if we're going to talk about knot theory, we don't care about bit strings, we care about knots, right? But the point is, a knot, in complexity theoretic knot theory, we really think of diagrams of knots, so pictures of knots, and that's a combinatorial thing, and it can be encoded as a bit string, okay? So while we have bit strings here, really we have in mind later that these bit strings will be encoding things we care about, either like graphs or knots or triangulated manifolds or simplicial complexes. The bit string can encode all kinds of interesting things. Okay. Now it will be important to remember in that encoding, like the length of the bit string is like the size of the bit string. We want to know how that compares to like the size of the combinatorial thing it's encoding. So we'll say some things about that in a second. All right, let's do some examples. So, all right, P, polynomial time computable decision problems. Okay, so what's an example of a problem in P? Well, I already mentioned one before, graph connectivity. So here you're given a bit string that's somehow supposed to be encoding a graph. All right, that's a kind of abstract. Let's just imagine I give you the, instead of giving you a bit string, I'm going to give you the adjacency matrix of a graph. So it's a symmetric 0-1 matrix. That represents a graph. And you can ask, is that graph connected? Well, as a function of the size of the adjacency matrix, which is something like the number of vertices squared, you can answer that question in polynomial time. Okay, you can do either a depth first or breadth first search to build a spanning forest, and then just test that thing's connected. So, something like that. So this is in polynomial time. And another example is primality testing. So in this problem, you are actually given a bit string, not something that we encode as a bit string. You're given an honest bit string that you interpret as a natural number in binary. Okay, so And then you want to know, is that number a prime number or not? So that problem can be answered in polynomial time. That's an important result from the early 2000s. So are there any questions about what I mean by polynomial time computable? Because this is going to keep coming up again and again.
I think it's okay. Yeah.
Cool. All right. So now the complicated one, NP, non-deterministic polynomial time. So what this means isn't that there's just a fast algorithm to answer the question yes or no. There's only a fast algorithm with some kind of assistance. Okay. So what we really have in mind here is that NP is an asymmetric complexity class. So P is kind of symmetric. If you can answer yes in polynomial time, then you could also answer no in polynomial time, kind of thing. So, but in NP, we only ask something of the instances of the problem where the answer is yes. Okay, so a problem is in non-deterministic polynomial time if all of its yes instances admit short, easily checkable proofs of their yesness. Okay, so this is not a technical definition. I could write down a technical definition, but it's a big mess involving Turing machines and stuff. So we don't need to go there. But maybe the best thing to do is keep in mind an example. Okay? And the prototypical example is called Boolean circuit satisfiability. So in this problem, you're given a bit string that encodes a Boolean circuit. So here's an example of a Boolean circuit down here. What is it? Well, it's a way of stringing together a bunch of ands and ors and not gates to build up a directed acyclic graph with exactly one output. And you can think of this as somehow being a function because it's, I can feed this thing like input like that. And then, so this 0, 1, 1, 0, that's a bit string of length 4. I can feed it to this Boolean circuit and output a single bit, right? So the not of 1 is 0, and of 0 and 0 is 0, the or of 1 and 0 is 1, then the or of 0 and 1 is 1. So look, I just found an input that makes the output equal 1. So because of that, I would say that this circuit Z here, it is what is called satisfiable. It admits an input that makes the output equal 1. Okay. And now we can build a decision problem using this notion of satisfiability. So the decision problem takes a Boolean circuit and it outputs yes if there exists an input to that circuit that makes the output equal 1. Okay. And otherwise, if I had a circuit where no matter what bit string I tried to feed into it, I always got a 0 out here, then we would say that circuit is not satisfiable. So the answer to the CSAT decision problem would be no for that circuit. Okay. So are there any questions about the definition of CSAT here?
So just to clarify, you want to find all the entries in order that the exit is always 1, or
I want to know, does there exist an input to the circuit that makes the output 1?
There exists. Okay.
Yep. And just to touch base with size and stuff, the size of a Boolean circuit is the number of gates you see. So here the size would be 4. We have 1 NOT gate, 1 AND gate, and 2 OR gates. So this thing has size 4. And this problem, to be clear, I do not have a polynomial time algorithm to answer whether or not this circuit here is satisfiable. All I really know is that if it were satisfiable, then there's some input that I could plug in that I could quickly check makes it satisfied. Here I got lucky. I just guessed 0, 1, 1, 0, and I got lucky and the output became 1. But there are lots of circuits where maybe there's only one input that makes the output equal 1, that makes the circuit satisfiable, but it's buried among exponentially many things. You have to go searching for it. Where is this input that makes it satisfiable? And P is kind of formalizing the property here that, like, well, okay, maybe you don't know which input makes it equal 1, but if there were one that made it equal 1, you could check that it equals 1. Okay. So that's NP. And this problem, CSAT, is is what's called NP complete. So it's a problem in NP, but it's also just as hard as every other problem in NP in a way that I'll make precise later. Okay. So there's a dual decision complexity class called co-NP, which is defined exactly the same way as NP, except we replace the roles of yes and no. So now these are the problems where for all of the no instances, if the answer to the instance is no, then there's a short proof that the answer is no. Okay. So the example here is Boolean circuit tautology, which is the opposite question to the satisfiability question. So in satisfiability, we want to know, is a given circuit have an input that makes the output 1? And now for tautology, we want to know, for a given circuit, is it true that it's a tautology? No matter what input you plug into the circuit, is the output always 1? Okay, so we would say a circuit is a tautology if exactly what I just said. So a circuit Z is a tautology, so the answer to the tautology question on Z is yes, if for every input to the circuit, the value of the circuit on that input is 1. Okay. So, and otherwise the circuit is not a tautology. What would that mean? If it's not a tautology, there's some input that makes the output equal 0, right? So it's not a constant function, effectively. Okay. And this is a different complexity class, and it's kind of remarkable, worth pointing out. These two definitions of NP and co-NP, they're asymmetric with how they treat yes and no. And NP and co-NP are really expected to be different complexity classes. There's no theorem because we don't even know that P and NP are distinct, but it's believed NP and co-NP are distinct complexity classes. Okay. So that's co-NP. And then there's some other ones. There's P space, which is polynomial space computable, and exponential time, et cetera. So they all fit together like this. So if something can be computed in NP, well, if a problem is in NP, then in fact, there's, that's not even really saying there's an algorithm to say it's an NP. It's saying that, like, well, there's a way to check given instances. If their answer is yes, then there's a way to check that it's yes. That's what it means quickly, but that's not really an algorithm to answer the problem. Okay, so to answer the problem, you have to search through all of the possible things that make it yes and decide if there is one or isn't. And you can do that in polynomial space. Okay, so there's a P space algorithm for things in NP. Okay, so that's all like some rather abstract stuff. I want to get into a couple more definitions, and then I'll talk about knots again. Okay. So these statements of the form like that I've just been discussing, that a decision problem L is in complexity class S, that's a kind of upper bound on the computational complexity of L. Because in order for L to be in complexity class S, it has to satisfy some conditions with respect to algorithms or something. So that's a kind of upper bound. It's saying there's some kind of algorithmic constraint on L. But it's just as important in complexity theory to understand lower bounds. So how do we formalize complexity theoretically what lower bounds are? And this is where what are called reductions. Okay. So a reduction from problem L1 to problem L2 is a polynomial time computable, I guess it would be a counting problem. So I'll just say it's a polynomial time function R from bit strings, which I'm just going to know 0, 1 star means the set of all bit strings. So it's going to be a polynomial time function that takes bit strings to other bit strings in such a way that I can convert instances of L1 to instances of L2. Okay. And now let's remember, what is L1? L1 is a function from bit strings to yes, no. And so is L2. It's a function from bit strings to yes, no. These are two different decision problems, and R is going to convert instances of L1 to instances of L2 in polynomial time. And what we want is this diagram to commute. So in other words, we want L1 to equal the composition of R with L2, or L2 with R. So that's what a reduction is. This is sometimes called a CARP reduction. It's a CARP polynomial time reduction from L1 to L2. Okay. And this is what this is saying morally, is that L2 is at least as hard as L1. Why is that? Because you can use, this is saying you can use L2. If you had a good algorithm to solve L2, then you would therefore also have a good algorithm to solve L1, because you have this way of solving L1 by converting using R to L2. So this is what we mean by lower bounds, okay? And then we get some definitions. So a problem, L is NP hard if for every problem in NP, so for every problem I'll call L prime in NP, there exists a reduction from L prime to L. And if L is in NP, so if L is a problem in NP and it's NP hard, then we say L is NP complete. And now it's like a classic theorem of Cook and Levin that I already mentioned from the 70s, that CSAT is NP complete. And what's cool is that like NP completeness is like a transitive relation. So you can, if you have one problem in NP, that's like in NP, that's NP. Well, you can compose reductions, right? So you can compose reductions, and that means that like you can prove, if I want to prove a given problem is NP hard, it suffices to reduce CSAT to that problem. So the corollary is that if to prove a given problem L is NP hard, suffices to find, you don't have to, right, because up here it says you have to find a reduction from every problem in NP to L. But Cook and Levin already did that for CSAT, and now you only have to do that for CSAT. Okay.
Sorry, Eric, could you CSAT, what is?
CSAT was the circuit satisfiability problem here.
That.
Yep. Okay. So that's just background. I'm sorry that took so long, but I hope it's worth seeing some of these definitions. So now I want to talk about examples in knot theory. Okay. So so I'm going to start with some simple examples and work our way up. Okay. So signature is an example. So we can think of this as a function from knot diagrams to the natural numbers, right? Or the integers, I guess, z. But we can encode z as like bit strings. Whatever, doesn't matter too much. So given a knot diagram, you want to compute its signature. What's the complexity of this problem? Well, it turns out signature you can compute in polynomial time. So it's this function can be computed in polynomial time. So we say signature is in P. And why? Well, because you can get the signature from the Seifert matrix, right? So you basically use Seifert's algorithm. Right, he says like if you have a knot diagram, you can quickly find a Seifert surface for the knot by like orienting. And you can build the Seifert surface by resolving the crossings in a given way and creating disk with boundaries, these red curves, and then gluing in strips this way, right? So you have the Seifert surface, and then, well, once you have the Seifert surface, you can find a set of curves that generate it, the homology of that Seifert surface, and then you can compute the signature you can compute the intersection pairing there and get the signature from that using linear algebra. Okay. So the signature, that's a simple invariant of knots. And it's a simple invariant, not only in the theoretical sense that it doesn't contain much information theoretically, but it's also simple to compute complexity theoretically. Okay. What's another simple invariant? Another one would be the Reith. You can compute that in P, right? The Reith is an invariant of oriented diagrams. So if you have I can do it. I think I did a figure 8 there. Given a diagram, you can compute the Reith quickly. So, from the diagram. So let me note here. The size of a knot diagram is its crossing number. Okay. So this has size 4, this one has size 3, and what I'm saying here when this is in P is like, well, there's an algorithm to write down the Seifert matrix that runs in time polynomial in the crossing number, and from the Seifert matrix you can then in polynomial time in that thing figure out the signature. Same thing with the Reith, given the diagram, well, you can orient, it has to be an oriented diagram to talk about the Reith, and you just, well, in this case, you can compute the Reith in linear time. You just say, well, that crossing's a minus or a plus, that one's a minus or plus, that one's a minus or plus, you just add them up. Okay. So that's pretty simple. Okay, so those are some kind of boring low complexity invariants. And then there's maybe more interesting questions we can ask. One would be the unknot recognition. So again, this is a function from knot diagrams to yes, no. And in this case, the answer, so K, so a diagram K will go to yes if K is an unknot. So if it's a diagram of the unknot, and no otherwise. So this is one of the most interesting questions in knot theory, right? How do you figure out whether or not it's an unknot? And moreover, what's the complexity of it? Of how quickly can I answer this question as a size of the diagram? And what's known is that this is in NP intersect co-NP. These are due to, who would this be? I guess Haas, Lagarius, Pippinger. Put it in NP, and then in co-NP, we have two different results, one of Cooperberg and then 1 of Lakenby. Okay, so what is this saying? This is saying, what does it mean for unknot recognition to be in NP? That means if the knot is an unknot, then there's a short proof that it is an unknot. Okay, and this uses what's called normal surface theory. And on the other hand, if a knot is not an unknot, you need to somehow prove that it's actually tangled up somehow. So you need to have some kind of certificate that certifies that the thing can't be untangled. And the way you do that are using Haken hierarchies. But question, is unknot recognition in P? This is one of the more important open problems in knot theory and algorithmic knot theory. And Mark Lakenby announced a result a little over 18 months ago. And said he had expected a paper to come out about a year ago, but that hasn't happened yet, so I don't know. So maybe. So Lakenby claimed yes at some point. And that would be amazing if it were. Okay, so my last few minutes, in my last 15 minutes or so, I guess, I will transition and talk about other invariants. Okay, so, right, this isn't really a question about invariants in some sense, right? But let me talk about group theoretic invariants. So here, what's the setup? So we have G as a finite group. I guess it could be an infinite group as long as the next thing we pick, C, this will be some complexity, some conjugacy class. And I'll typically assume it's non-trivial, meaning that it's not just the conjugacy class of the trivial element in G. And then given a oriented diagram K of a knot, I'll define HKGC. This is going to be the homomorphisms from pi 1 of the knot to G that send a meridian of K it should map to the conjugacy class C. So for example, when G is D6, the dihedral group of order 6, and C is the reflections, then HKGC, this is the Fox 3 colorings of K.
Eric, what is the meridian of a knot?
Yeah, so I just mean whenever you have a diagram that's been oriented, once it's oriented, I can make sense of a meridian by just saying, use like a right-hand rule. So like point your thumb in the direction of the orientation and then like take a curve that winds like a given direction. So any curve in pi 1 that's in this conjugacy class of that red curve is a meridian. Does that make sense? So it uses the orientation. Yeah, it's just a small curve that winds once around the knot in the pi 1, but you have to decide whether it winds clockwise or counterclockwise, and that's why you need the orientation. Okay.
So it has to be the same for one connected part of a link?
Well, I'm only talking about knots for that reason. So I'm not going to have multiple components. So I'm just going to assume like one component. But okay. So, but in any case, everything I've done here sets us up to define an invariant. So given G and given C, we get an invariant of K that's a natural number. And as I tried to warm up to in the beginning of the talk, we can ask ourselves, what's the computational complexity of computing this invariant? So given G and C, so given some fixed G and C, what is the complexity of computing this number as a function of K? Or more precisely, as a function of the crossing number of K. And we can talk through some simple examples, and then I'll say some other things. So the first example is that G is abelian, in which case C is supposed to be a conjugacy class of G. So C would just be a single element. And then in this case, HKGC, the number here, well, it's going to be the number of homomorphisms from pi1 of K to G that send a meridian to C. But it's not hard to see that there's going to be exactly one of them. Okay. And the reason why is that, well, because G is abelian, any homomorphism from pi1 of K to G will factor through the abelianization. And the abelianization of the fundamental group of a knot is always isomorphic to Z. And moreover, it's generated by the meridian. So the fact that the meridian has to map to this group element G forces us to only allow one possible homomorphism. Okay, so this is a trivial invariant. Therefore, it can be computed in constant time. Doesn't matter how big K is, we can compute this. It's always one. You just compute it in constant time. So a more interesting example is G metabelian. For reasons related to the Alexander polynomial, this can be computed in polynomial time. Basically, you use the Alexander module. Because this is metabelian, the Alexander module knows all of the information you need to know to count maps to metabelian groups. And well, the Alexander module can be computed in polynomial time from K. So I'm not going to say too much more about that. And then these are, so stress again, these are in some sense both upper bounds and lower bounds, right? It's trivial invariant, that's dumb. So there's nothing to say there. This can be computed in polynomial time. And well, like you could ask for logarithmic time or something, but like you don't really need to, right? We're pretty satisfied with polynomial time. That's considered efficient. So if you have a polynomial time algorithm, to first approximation, there's no more interest in complexity theory. So you're done. You don't need to worry about lower bounds. Okay. But now what about other G? Well, let me just say in general, I do not know. But the theorem, an older theorem of mine with Greg, is that if G is a non-abelian simple group, then deciding if this number, HKGC, so it's always going to be at least the size of C, but deciding if it's bigger than that is NP hard. In fact, it's NP complete. So yeah, I guess I don't have too much time, so I won't go into the proof of this. But this leaves a question. Okay, so we have an answer for abelian groups. We have an answer for simple groups. And then the question is, what's going on in between? So, the question here is there a dichotomy result? For GC. So what I mean there is it true that this number, HKGC, is either computable in polynomial time or it's NP complete? If so, what conditions on G and C determine which case you're in? Okay, so this is all supposed to be warm up to analogs of this question in the TQFT setting. Okay, so I'll spend the last, I guess, 4 minutes discussing this. So, I'm definitely not going to do justice to this, but in general, the idea of like Kataev, Friedman, Larson, and Wang is that every modular tensor category C yields, let me say unitary, it yields a unitary TQFT, and hence a model for a topological quantum computer. So, however, the strength of this quantum computer depends on the category C. Okay. So for example, the result of Friedman, Larson, and Wang is that when C is the category of representations of the quantum group, SL2, where Q is a root of unity, of order not equal to 1, 2, 3, 4, or 6, these invariants the topological quantum computer based on this category is universal, or well, you might say fully quantum programmable. And at the end of the day, this is what this is really saying is something about the computational complexity of the Jones polynomial, of evaluating the Jones polynomial. That is what the computer is doing. They have the following question. So you could take BQ. This is a function from knot diagrams to C that takes the diagram and gives you the value of its Jones polynomial at Q. Okay, so that they're basically using this function, this invariant, to build a quantum computer. And it's fully programmable, whatever that means. I could say more if people are interested, but it's not always the case that it's fully programmable because in this case of UQSL2, where Q is not one of these roots of unity, but it's not always fully programmable. So another example would be, I could take the category to be what's called the category of representations of the Drinfeld double of G. Okay, and now in this case, the invariance, the topological quantum computer here is computing these kind of generalized HKGC invariants. And these things, while they can be NP hard, they can't be used for fully programmable quantum computation. Okay, and so I guess I'll finish with just a question, and I can get into more details if people are interested. But the question is, given the modular tensor category C, what is the computational complexity of computing TQFT invariants of knots associated to C? So maybe the Reshetikhin-Turayev invariants of knots. So in other words, like Reshetikhin-Turayev of C, we can think of as a function, again, from knot diagrams to C, that sends a diagram to the value of the Reshetikhin-Turayev. Maybe you have to color it by an object in C or whatever, I won't bother. Has to do something like that. So, and one wants to know, what's the complexity of this invariant? And is it complex enough to be able to support fully programmable quantum computation? So I'm not going to say much more about this other than just superficially. So just as before, we can really think of this as a generalization of the question I asked before for finite groups. So here, you want to know what are some simple conditions on the group and maybe the conjugacy class that tell you whether this invariant can be computed quickly or whether it's NP complete. So it would be great. So one guess, for example, is that the group has to be non-solvable. So one might expect here a dichotomy result along the lines of that, like, well, if the group is non-solvable, then this invariant is NP complete. Otherwise, if it is solvable, then you can compute it in P. So that could be the kind of dichotomy result one has here. And what would be great is if one could formulate and establish a dichotomy result for topological quantum computers in terms of tensor categories. So this is, Eric Rowell spoke here in the seminar a couple weeks ago, and this is stuff he's had much more insightful things to say than I have today. So, for example, he has a conjecture that with Deepak Naidu that says that if C has if C is what's called weakly integral, meaning its quantum dimension is a square of an integer, then the topological quantum computer based on C has what's called property F, which is similar to this thing, and therefore cannot be used to build a fully programmable quantum computer. Now, what's very interesting to me is whether, so that's a kind of no-go result, saying that if C has a certain property, then you cannot build a fully programmable computer. But it's sensible to also just guess, like optimistically, like, well, maybe if C is not weakly integral, then maybe it can always be used to build a fully programmable quantum computer. I don't know that there are no examples of things that are intermediate. So I would expect a kind of dichotomy result here as well, along the lines of things Eric Rowell has worked on. So let me stop there because I'm already a little over. And people have questions. I'm happy to say more, especially about the quantum stuff here. Cool.
Thank you, Eddie. Thank you very much.
Thanks, Carlos.
Yeah. So I think we passed by to the questions. Yeah. Is there any question by the audience? I can start with some questions. Well,
sure.
I have a question that is more related with what you say in the abstract, that if we add some group of gauge symmetries, then we not can create a more powerful computer. But then you are interested in this, in this invariants, the A, K, G, C, that is all the homomorphisms from the fundamental group of node. Right. We arrive to some specific group, and you want to classify the complexity of the calculation of these invariants. And right. From something that you start from the abelians that has polynomial time of computation, then you arrive to the simple group that has some NP complete. So what you are interested in that we know all the invariants from node that are the Kaufman bracket, the Jones polynomial, the Kovanov homology. So why are you so interested in this specific invariant? Yeah, and then how this not create a better quantum computer?
Yeah, so good question. Yeah, so first of all, I wouldn't consider Kovanov homology in the same vein, right? So Kovanov homology is like a categorification of the Jones polynomial, which is extremely interesting to be sure, but it is not a Reshetikhin and Tarayev invariant. So I did not say much at all here, but the real point that these guys made is that whenever you have a 2+1 dimensional unitary TQFT, you could try to build a quantum computer with it. And then the question is, how powerful is that quantum computer? Okay. Now that has nothing to do with tensor categories, except that 2+1 dimensional TQFTs, as long as they're like once extendable and semi-simple and stuff, they're determined by modular tensor categories. So you can really treat the modular tensor category as like the seed, the kind of algebraic data that determines the TQFT. And therefore, but if the modular tensor category determines the TQFT, then in particular, it should know, we have to figure out how it knows, but it should know something about the complexity of the invariance of knots that the TQFT supports. So that's why I'm interested in these invariants, because there's a huge class of them. Every modular tensor category gives you a different Reshetikhin and Tarayev invariant. And So it's a very large class, but at the same time, they're pretty well structured, right? So, where do these things come from? Well, there's tensor categories like this, UQSL2, that come from quantum groups. And then there's tensor categories, modular tensor categories like this that come from finite groups. And I don't know, there's some other things like the Hagerup category, I guess. I don't know much about it, but roughly speaking, most modular tensor categories people are able to understand and have discovered are some combination of these things and quantum group things. And the hope is that, like, well, there's structure theorems about tensor categories, things like Eric Rao spoke about and Julia Plavnik spoke about last week, and Cesar. So, these people are actually talking about the algebra, the very important algebra behind these things that gives some structure theory for modular tensor categories. But the hope is that, like, not only do you get abstract algebraic structure theory, but you can use that algebraic structure to tease out the complexity of the invariants. And that's why, because there's a lot of cool algebra. I care about this because there's a lot of cool algebra, but it's also exactly these invariants that are pertinent to topological quantum computation and things like topological phases of matter and the quantum Hall effect, things like that. So Kavanagh homology, not so much, right?
But then you are providing more structure in your cohorts category, that you have the nodes, and then this homomorphism from the fundamental group to the group have more structure. You are promoting to a G equivariant version or something like that.
Yeah.
So you have
what,
another Jones polynomials and that kind of things. In that depends of your model category.
Yeah, so maybe I'll just say a little bit more about what I promised in the abstract and failed miserably at getting to today. So there's this construction called gauging. Okay, so it's a kind of so you start with a modular tensor category. And you also start with an action of a group G on C, okay? And gauging is a way of building new modular tensor categories from given ones with group actions. Okay. And it's a pretty general phenomenon. It's a good way to start sifting through and relating different tensor categories to one another is by gauging and de-gauging. So there's a process here where from this, so you start with this data, and then assuming certain obstructions vanish, is you can build, I don't know, this thing. So this is a G cross modular tensor category. And exactly what you're saying. So this thing, so modular tensor categories give you TQFTs. G cross modular tensor categories give you G equivariant TQFTs. So you're exactly right. You no longer have a TQFT from the usual Bordism category. You have a TQFT from a kind of Bordism category where everything's equipped with a G bundle. And so a G Bordism category. And so that's the first step in gauging. And then you do something called equivariantization. And you get back an honest modular tensor category. And it's somehow bigger than C because it's taken C and coupled it to G. So an example, you could start with VEC with the trivial G action. And then the gauging will create DG mod. Okay. And so, you're taking something small with some trivial information and gauging, but then you're getting something non-trivial. And a basic question is, how does the complexity of how did the complexity of the gauge invariance relate to the complexity of the original invariance? And what's cool is there's something I wanted to discuss but did not give myself enough time for, is that there's a decoupling. So even though, for example, I told you that when G is a non-abelian simple group like A5, well, counting homomorphisms to A5 is NP hard. And that's saying something about the invariance of DG mod when G is A5, that they're NP hard. So this gauging is going from something that's like trivial. The VEC supports only trivial invariance. It's a trivial TQFT. Everything gives you the invariant one. And but when you gauge by the trivial G action, you get DG mod, which is a has non-trivial invariance. They're highly non-trivial. If G is A5, they're NP hard. Okay. However, the result is that even though this invariant can be more complex than this one, it can only be more complex in a classical sense. Okay, so this is classically a harder invariant. However, it is not quantumly it does not lead to a more powerful topological quantum computer.
Oh, okay. Please.
And that was the real punchline. I should have built into the talk better, but that's, yeah.
That's a nice resolution.
Yeah.
I don't know if there is a question by by other people. Just raise your hand or.
And this is work in progress with Colleen.
Gerard?
Hi, yes.
Yeah.
Thank you so much for the talk. It's just a naive comment. One would expect complete invariance of knots to be more complex or have higher complexity.
Of course. Yep.
Is there a theorem like that, that if it's a complete invariant, it must at least be in this level of complexity?
So let me, no, but let me explain why. So here's an example of an invariant. The isotopy class of the knot, that's an invariant, right? So I could have a function that takes a knot. And what do I really mean by that? Well, you might imagine some procedure that builds a table with one entry from each isotopy class of knots. And what you could do is associate a knot, its spot in the table. Its number, what number in the table is it? What entry of the list is it? Now it's an infinitely long list because there's infinitely many isotopy classes of knots, but you could ask, well, given the diagram, which entry on the list corresponds to the unique preferred representative? And you can imagine a Rolfson knot table, except it's infinitely many pages. And you just want to know which entry is this thing. So that's a complete invariant of the knot, but I don't know anything about how to compute that thing. So a complete invariant, necessarily computing a complete invariant is going to be equivalent in complexity to the problem of solving the equivalence question.
I see.
So the equivalence question would be, given two different diagrams, are they isotopic? So the reason we don't have an answer to your question is because we don't have an answer to the question, what is the complexity of the not isotopy question?
Right.
Okay. And I can say some things. So what is known is that there is an algorithm. So there's some algorithm. The running time is something like, so what do we have here? We have two knot diagrams, K1 and K2. And we'd like to know, do they represent isotopic knots? Now, let me point out that Reitemeister himself gave half an algorithm. he said, well, if they were isotopic, then there's a sequence of Reidemeister moves that you can use to see that they're isotopic, right?
Mm-hmm.
But if they're not isotopic, you don't know, you can't just, there's infinitely many possible sequences of Reidemeister moves, right? So unless you get an upper bound on how many Reidemeister moves are required, the Reidemeister theorem is only half of an algorithm. Okay. So what is cool is that there are upper bounds. People have proved that since then. Okay. So, and what's known is that the running time is something like this. So it's a tower of exponentials, where this, we don't really know how tall it is. I don't know, it's like 10. It's a constant. So there's nested, this is basically saying there's nested loops inside the algorithm. And this is kind of how many nestings there are roughly. Yeah, and then these are the crossing numbers. So it's some iterated tower of exponentials in the sum of the crossing numbers.
Cool.
Yeah, but it's expected you could do much better. I would expect. So maybe in P space, which would imply an exponential time. If it were in P space, it would be an exponential time. So that would be cool. Yeah.
Mm-hmm. Thanks. And what about volumes of hyperbolic knots? Is there complexity known?
Yeah.
Because
so there's
to give a triangulation of the manifold and then try to calculate the volume.
Yeah. So there's a question here of input. What form is the input in? So are you giving me a knot whose complement has been triangulated with a geometric triangulation? So I have all the geometric information already. Well, if I have that, then I expect I should be able to get, there's this issue of computing these Lobachevsky functions, right? But you could get an approximation to the volume I would expect in polynomial time in the size of all of the geometric data you gave.
Mm-hmm.
Right, but that's a different question from
triangles and right. Okay.
Because you may have imagine you could have, maybe the knot only has 14 crossings, but you told me you're giving me all the geometric data. So you're giving me not just the diagram, you're giving me the triangulation where each of the simplices has dihedral angles. And, so we have to keep, that's all part of the input in that case. And, it becomes an easier question because the input is bigger.
Right, yeah, no, I see. It's more difficult to actually compute the triangulations, I guess.
That's right, yep.
Yes. All right, thank you so much.
Sure.
Yeah, thank you very much for the question. If there are not any other questions,